Hello and welcome back. Today we're talking about simple machines. So a simple machine is any device that acts to increase or decrease the amount of force output by the machine compared to the force you input into the machine. So while this is possible and happens all the time, it should be noted that while we are changing the amount of force out as compared to the force we put into the machine, it should be noted that the total amount of work put into the machine will be equal to the amount of work done by the machine. That's in the case of a perfect machine without friction. If there is friction, then the amount of work that the machine can do will be reduced by that friction. And so, if there is no friction, then we say that the work that we put into the machine is going to be equal to the work that's coming out of the machine. And since work equals force times displacement, we can see that the work in becomes the force in times the distance in, and the work that comes out of the machine is going to be equal to the force that the machine puts out over the distance it puts it out. And so, rearranging this equation, we get this. D in over D out. What I've done is divided both sides by D out. That's the distance over which, this is the distance over which we put effort into the machine. And D out here and here is the distance over which the machine provides effort. So D in over D out equals F in over F out. This is the force we put into the machine, the amount of force we put into the machine, divided by the amount of force the machine puts out. And so, seeing as these ratios are inverse, what we get is that using these machines is a simple trade-off. If Fn times D in equals F out times D out, then we can see if these two are going to be equal and F out is to be greater than F in, then D out must be less than D in. And so what that says is, if you put in a little bit of force and get out a lot, then what you have to do to compensate for that is to put your small amount of force in over a larger distance. And what's going to come out? You'll get a larger force, but it will come out over a smaller distance. This is just the conservation of energy. With work being a kind of energy, the force you put in, if it's small, means that the distance you put it in over must be large. You can apply a smaller force, but you have to apply it over a larger distance. Now, when we're talking about machines that are perfect, that is to say, machines that experience no friction, this is also valid to talk about when you're looking at machines with very little friction compared to the loads they carry. When we're looking at ideal machines, we can define something called the ideal mechanical advantage. This is the mechanical advantage achieved when there is no friction. IMA is expressed as the ratio of distance in to distance out. So IMA equals D in over D out. Now, for a perfect machine, for a perfect machine, IMA will also equal F out over F in. Now, we know that there are no exactly perfect machines, so let's keep our definition of IMA to this. IMA will equal D in over D out. That's the distance you apply force to the machine divided by the distance the machine applies force to a load over. Now, since the D in and D out, since those are happening over the same time periods, while you're applying force over your D in, the machine is applying force over the D out. Since those are happening at exactly the same time, since they take the same amount of time to happen, we can divide both top and bottom by time and come up with a velocity. Velocity just being distance divided by time. And so, the IMA is sometimes referred to as the velocity ratio. Now, those are ideal machines that we were just speaking about. When it comes to actual machines, there are differences. Now, it's true to say that the amount of work put into the machine will always equal the amount of work coming out of the machine. However, not all of that work will go into moving the load that you want to move. And so, when you put a certain amount of work into the machine, you will get that amount of work out, but not all of it will go to the load. Some of that work will go into overcoming friction, which will have the effect of creating heat. Some of it will go into distorting the material, whether elastically or plastically. And not all of that work can go into moving your load. So this work isn't lost. It still happens. It's just not very useful. That can happen in a machine. We can talk about actual mechanical advantage. Now, we can't predict the amount of unintentional work that's done due to wasted energy. However, and so when we want to measure the real work output from an actual machine, what we have to do is measure it. And so we define the actual mechanical advantage, or AMA, as the ratio of force output to force input. And in a real machine, this will always be less than the ideal mechanical advantage. It'll always be less than the distance in over distance out. And so we can define AMA as equal to F out over F in. We should also note that AMA is always going to be less than IMA. And now knowing IMA and AMA, we can talk about the efficiency of a machine, which is the ratio of IMA to AMA. And so for an idealized machine, which has no mass, which has no friction, the efficiency is going to be 1. However, real machines do have mass and do have friction, and so efficiency for a real machine is always less than 1. So efficiency equals AMA over IMA, which equals the work output by the machine divided by the work input to the machine.